We've been waiting years for the next evolution of CPU design, but everything points to 2019 being an exciting year for processors. Welcome to another episode of Upscaled, where we take a look at the components and bits of tech that make our favorite gadgets better. If you missed our first episode on ray tracing and Metro Exodus, go check that out. We asked if people were excited about that game because of ray tracing, and while a few of you picked up the new RTX graphics cards at launch, it seems that most folks who upgraded did so because they were already in the market or their old cards died. And there are a lot of you out there also who intend to use your 1080 Ti cards until the sun burns out. One person did make the great point that if we are currently getting 1 ray per pixel in that game, with Moore's law and computer power doubling every 2 years, we could be at the 16 rays per pixel minimum that Pixar recommends within a decade. Except here's the thing. Moore's law started to break down around 2012, and that's part of what we wanted to talk about today. Processors are still getting faster, but the pace of improvement has slowed way down. After years of incremental change, 2019 might be a big year of improvements though. We'll be at Computex, where we're expecting to see new designs from AMD, and Intel has promised new chips later this year as well. So here's what's going on. Moore's law, which is actually more of an observation of trends than any sort of real law, is more about the density of transistors on a chip than speed, but the one can serve as a decent proxy for the other. Coupled with another law called Dennard's scaling, it says that roughly every 2 years, the number of transistors on a chip should double, and that should make the chip about 40% faster while using the same amount of power. This held true for much of the history of the microchip, but in the last 15 years, it's kind of gone off track, and chips haven't gotten nearly as fast as predicted. Now, there are a few reasons why, but a big one is that to cram twice as many transistors into a given space, you need to make them smaller, and engineers have been struggling with this in recent years. Modern chips are made almost like exposing a photograph by projecting a pattern that writes the transistors onto a silicon wafer. Transistors have actually gotten so tiny that they are smaller than the wavelength of light used in this process. And to compensate, multiple patterns are used and projected and overlapped, writing and overwriting to create tinier and tinier features. The more complex a chip and the more patterns used, the more likely there are to be errors or defects. After all, if you're trying to make transistors that are measured in the billionths of a meter, a tiny misalignment in patterns will make a mess of things. Beyond this, some features of a modern CPU are already around 10 atoms across. And not only is this super hard to manufacture, but at this scale, quantum effects make it hard to get electricity to behave. Things get weird, and it's tricky to control the electricity flowing through the chip. If you want to know more about this, let us know, and we'll do a future episode on transistor design, voltage leakage, electron tunneling, all this sort of stuff. Now, with all these challenges, companies have adapted by cramming more and more cores onto a single chip. But this only speeds up certain workloads, and it introduces its own problems. Putting lots of cores on a single processor means you need to physically manufacture a big chip, or die, as they call it. This has 3 big issues. First, the bigger the chip, the more likely there are to be manufacturing errors. Second, it's harder to dissipate heat from a big chip. And third, big chips are just more expensive to make. Cramming a lot of cores onto a die also doesn't solve the issue that by themselves, CPU cores just haven't gotten that much faster. Single core speed still matters for a lot of programs, from animation to gaming, and on a per core basis, an Intel 8700K from last year is only about 25% faster than a 4790K from 2014. So that's the problem. It's getting harder to cram more transistors into a core, and just adding more cores to a CPU doesn't fix everything, and it introduces its own problems. Fortunately, AMD and Intel have both proposed solutions. Their approaches are different, but they all revolve around breaking up the CPU into discrete chiplets and connecting them together to form a sort of Voltron CPU. Modern CPUs are usually monolithic. Every bit of them is formed from a continuous piece of silicon. Each part of the CPU, including the processor cores, the GPU, memory controllers, input-output, the cache, it all has to be built on a continuous piece of silicon, and if any of those parts are defective, the chip might be a total loss. What Intel and AMD are proposing is to manufacture these parts of the CPU separately and then assemble them together. As companies are struggling with new processes to make their chips with even smaller transistors, breaking a CPU into chiplets could give them a big advantage. One of the issues with new manufacturing techniques to make smaller transistors, called a node, is that in a new node, typically lots of the processors come out defective, at least at first.
So we're trying to make a perfect wafer where every one of these is functioning, but that's rare. So we're trying to improve the process all the time and find out why the bad die in this wafer fail.
It's like this. If any given transistor has a chance to be a dud, the less of them you need to put on an individual chip, the less likely that whole chip is to be bad. By splitting a big chip into multiple smaller parts, companies may be able to hedge risk. If just one bit of the chip goes bad, they can just replace it and still have a working processor. These new nodes have been worse than most. Intel has been struggling for years with its 10nm node, and a few years ago, yields of working chips were rumored to be less than 10%. But we've since seen mobile chips like the Snapdragon 855 and Apple's A12 hit the market using a 7nm process. There's two things at work here, one of which is that node names are mostly marketing nonsense, and Intel's 10nm is actually denser than competitors' 7nm process. But also, part of the reason for this may be that mobile chips are tiny compared to a CPU and are easier to produce without defects. After all, with less transistors per chip or a simpler design, there's less chance for errors. By splitting a chip into multiple parts, the CPU makers can benefit more from smaller dies and more efficient manufacturing. Combining multiple dies into a so-called multi-chip module isn't new. Some early quad-core chips, like the Core 2 Quad, were built like this, as is AMD's Threadripper. But what AMD is doing with its next chips is a little different. Now, we won't know everything until AMD officially launches its Zen 2 line, which we expect to be at Computex in May, but based off what we know about their Rome server chips, here's what we're expecting. The CPU cores, where speed and power matter most, will be built at 7nm, while the memory controller and inputs that connect the CPU to the rest of the computer will be built at the reliable 14nm process the company has been using for years. This mix and match approach should maximize the bits of the chip that need to be speedy while minimizing the number of transistors that need to be built on that new process. While AMD looks to be trying to boost the limits of CPU performance, Intel, for now at least, is taking a different tack. They're talking about modular chiplet design as well, but so far what we've heard has been targeted towards the low power market. Intel is calling its new design Foveros, and it's a combination of splitting a processor into chiplets along with stacking multiple dies and memory controllers onto one chip. The idea is that instead of one monolithic chip, Intel plans to produce a CPU that uses one larger, higher powered chiplet and then multiple lower powered atom-based chiplets. This big little arrangement of high and low powered chips is similar to how many mobile CPUs are designed, with the little chiplets handling background tasks and the big chiplet doing the heavy lifting. Intel plans for all of these chips to be made with its much delayed 10nm process, but is planning to leverage the smaller transistors for improved power efficiency more than raw speed. Beyond that, I/O and memory controllers should be made with the more stable 14nm architectures. This seems like an evolution of Intel's Embedded Multi-Die Interconnect Bridge, or EMIB, which, like AMD's design, was a way to connect multiple chips from different manufacturing processes. But Foveros takes things a step further by stacking chiplets and memory on top of each other. There are potential upsides to this, a smaller footprint and better latency by putting the memory and processor into contact with each other, but it remains to be seen if this design can dissipate enough heat to scale to higher powered chips. Intel is calling its first Foveros chip Lakefield, and we should expect to see it sometime in the second half of this year. Then again, we've been expecting 10nm chips from Intel since 2015, so it might be a while. We'll be on the ground at Computex, where we expect AMD's new chiplet designs to be fully unveiled, and we'll be following Intel's progress towards a legit 10nm chip this year as well. Let me know if there's anything around CPUs you want me to dig into, or any announcements you're excited for from Computex, and subscribe to Engadget to get all those updates.